Alright, so one of the reasons why I picked to go into statistics is because by nature I analyze everything, whether it's myself or other people or the world. And so I was really drawn to the fact that in statistics you can use your ability to analyze to kind of not focus on the things that I usually spend all of my time analyzing. And so today I kind of want to talk to you about one of the things that statisticians do to analyze data, and that is to look for relationships, which we call correlations. And the simplest way to do that I found is by using a scatter plot. This is what a sample scatter plot looks like. It has an x-axis and a y-axis. So through the rest of the talk, I'll kind of go through like the points of the scatter plot, what the x and y-axis mean, and then I'll go through what correlation looks like on a scatter plot, whether it's positive, negative, or none. And then I'll kind of go through a really easy example. So for your scatter plot basics, just a quick review. On your x-axis, you usually put your independent variables. On your y-axis, you put your dependent variables, which we as statisticians call response variables. That's what we're measuring the relationship to the data on the x-axis. We want to see how that's changing. You could also have an instance where you have more than one variable on the x-axis, which is what this is showing. But I didn't really want to go into all that detail, so I kept it pretty simple. Correlations are valued at either -1, meaning negative, perfect negative correlation, all the way up to a +1, which is a perfect positive correlation, and a bunch in between. Here's an example of what a perfect positive correlation looks like. This never happens in my experience through all of my classes. It's my goal to someday see that in data. I'm not sure if that means I win $1 million or not, but maybe. Here's a high positive correlation. You can clearly see with your naked eye that there is a trend going upwards, which just is saying that as the variable on the x-axis goes up, so does the variable on the y. I didn't really like this picture of the low positive correlation because it's my understanding that you can't always see the correlation with your naked eye, and in this instance you can still, but I'll get to that in a little bit. Just go quickly again through the negative correlations. It's kind of the exact opposite of the positive. The trend is going down, which means as the x variables are going higher, the y variables are going down. Again, a high negative correlation, a low negative correlation. I, again, don't think you should be always able to see this trend with your naked eye. Here's an example of having no correlation, which means your correlation value would be 0. It's a horizontal band that goes straight across from left to right. Or you can have a vertical band that goes up and down kind of in certain areas. Or you could just have a big mess that when you add a trend line, which we'll do later in our example, it just kind of stays flat. So now I'm going to talk about my example. I found an easier example online than the one I came up with, so I kind of went with it. What they're trying to do here is they're 12 days of ice cream sales for, we'll call it Yee Parlor. And the independent variable on the x-axis will be our temperature over those 12 days. And they want to see if the temperature of outside changes their sales for ice cream, which is why ice cream sales would be on the y-axis. After plotting my data points, I get a pretty obvious positive correlation. It's clearly not perfect, because like I said earlier, that rarely to never happens. And I kind of briefly spoke earlier that sometimes when you can't see it with your naked eye, that you have to add a trend line, which is I went ahead and did that just to show you, even though you could see with your naked eye what that would look like, in the event that your data doesn't clearly spell out for you what the correlation is. In the package I used was JUMP, and it also gave me a value for our correlation, which I'm not going to get into today, but we call it the R-square number. And here it's a 0.9, which is very close to a 1. questions?